In this video, we will explain how to go step by step in solving our first light equation problems. So let's begin with looking at our tools. Of course, in the previous lesson, we discussed about how light is a wave, and it is a wave actually in an electromagnetic field. So it's a wave produced by whenever you have a charged particle that gets excited. So we focused on charged particles getting excited, specifically the electron. And if an electron falls back to its original energy state, it will emit a photon of light, which we're seeing right here as a wave. Now, it's important to note that light, as an electromagnetic wave, has a certain wavelength. So as we can see, the frequency increasing here. Notice as the waves become more frequent per unit time, the wavelength gets smaller. So if I can just pause this, so one wavelength is one crest and one trough. So one complete wave cycle would be measured as one wavelength. So as the wavelength of light gets smaller, its frequency increases. So notice this is a smaller wavelength than the previous one, and therefore it occurs more frequently. So this is represented in our equation. C is equal to lambda nu, where lambda is our wavelength measured in meters, and nu, our frequency measured in per second or hertz. Per second and hertz are the same exact unit. There is also our energy equation, which tells us how much energy that single photon, lowercase p, of light has, and that will be equal to h times the frequency. So we have two constants here. C is a constant, which is the speed of light. The speed of light is 2.9979 times 10 to the 8th meters per second. And the other constant is called Planck's constant, which tells us how much energy that a single photon of light can have by virtue of its frequency. And that Planck's constant is 6.626 times 10 to the negative 34th joule times second. We say joule second, not joule per second, but joule times second. So let's begin with a certain problem. So this first problem says violet light has a wavelength of 410 nanometers. What is the frequency? So in order to solve these problems, this video is going to show step by step how we should do this. The first step is to identify your variables in the given problem. In the problem, it said it had a wavelength of 410 nanometers. Whenever possible, you should represent the words by the symbol. So wavelength is this symbol lambda. And so that is equal to 410 nm. And in the problem, we're being asked, what is the frequency? Again, represent that by the symbol, nu. So once we have done that, that will allow us to then determine the tool we need in order to solve this problem. But before we can use our tool, we need to convert this unit, this physical quantity given to us, to the base unit. So base unit is what we're using, the last letter right here, what we're using to measure in. So in this case, since we're measuring length, it should be meters. Sometimes it might be seconds, sometimes it might be units of energy, joules, sometimes it might be per second, like in frequency. But we need to get rid of this nano. But nano means something very specific, and this is part of your toolbox right here. And if we look right here, nano, lowercase n, of course means 0.00000000001. Now, that is not convenient to work with. So we will always use scientific notation when we can. And so that is 10 to the negative ninth. Now, what's convenient about converting is that nano means 10 to the negative ninth. All I have to do is substitute in for lowercase n 10 to the negative ninth. And now I have lambda is equal to 410 times 10 to the negative ninth meter. Now I can focus on figuring out the rest of the problem. So the third thing I need to do is identify the equation I need to use. If I have lambda and I'm looking for frequency, I look at my two equations provided. Of course, this does not have lambda in it. It does have frequency, but I am not solving for energy. Here, this equation has lambda, we're solving for frequency, and we know C. C is the constant provided. So now we can rearrange this equation to solve for frequency, for nu. So let's go ahead and do that. We would divide both sides by lambda, right? And lambda over lambda is equal to 1. And so we can solve for nu. Nu is equal to C divided by lambda. You always should, when possible, rearrange your equation to solve for what you intend to solve for. In this case, frequency. And notice how that makes things a whole lot simpler in our next step, which is we substitute into our equation. So we're solving for nu. We have C and we have lambda. And now all we have to do is put this into our calculator, making sure that we use parentheses when we're doing that. And of course, the answer should be 7.3 times 10 to the 14th per second. So that is the frequency of this violet light, that the wave cycle occurs 7.3 times 10 to the 14th times in every second. Let's do another problem. In this problem, we're asked what is the wavelength in meters of the electromagnetic carrier wave transmitted by the sports fan radio station at a frequency of 640 kilohertz. And so we're solving for wavelength, which is in meters. So okay, at first we must identify our variables. We are being told that it has a frequency of 640 kilohertz. So nu equals 640 kilohertz. And we're being asked for what is the wavelength. So wavelength equals question mark. We should first simplify this given variable so that it is in the correct base units. So here, 640 kilohertz. If I look up kilo, K is 1,000 or 10 to the third. And we can substitute right in for kilo, 10 to the third. And of course, hertz means per second. So this frequency is 640 times 10 to the third per second. Now we can look for, in our toolbox, to find the correct equation to use to solve this problem. And of course, that's C equals lambda nu. But what's different in this case from the previous problem is that we know nu and we need to solve for lambda. So now we can rearrange this equation, dividing both sides by nu, and we can solve for lambda, and lambda is equal to C divided by nu. If we now substitute in for these variables, of course this C is constant, it is not a variable, but we substitute in for nu, the variable. So C is 2.9979 times 10 to the 8th meters per second, and nu 640 times 10 to the third per second. If we substitute, if we place this into our calculator, We can simplify, and we get 4.7 times 10 to the first meters. Let's take another. Here, calculate the energy of a photon of radiation with a frequency of 8.5 times 10 to the 14th hertz. So first, we must identify our variables. Again, we are given a frequency, nu, of 8.5 times 10 to the 14th hertz, which is per second. And we're being asked to solve for energy. So I've already converted to the base unit, and I can continue on to the next one. And looking at my tools, right, I'm solving for energy. So I will not need this equation. I will need this equation. Energy is equal to h nu, and I have nu. So now I can, well, I don't need to rearrange my equation. I can go right ahead and substitute. So E is equal to h nu, where h, Planck's constant, is provided, and we have nu, the frequency. And so we can substitute, and of course put that in our calculator, and we get 5.6 times 10 to the negative 19th joules of energy, a really tiny, tiny quantity of energy. Let's take one more problem. Calculate the energy of a photon of radiation with a wavelength of 6.4 times 10 to the negative 7th meters. So first we identify our variables. In this case, we're given wavelength. Wavelength is equal to 6.4 times 10 to the negative 7th meters. So different from the previous problem, where we were given frequency, we are giving lambda wavelength in this case. Of course, we've already converted to the base unit, so we can skip that. And we can identify the equations we need. Well, we're solving for energy, and energy is equal to h nu. But we don't have nu. We have lambda. And like in a previous problem, we determined that nu is equal to c divided by lambda, because we rearranged this equation. Well, if we have these two relationships, we can combine to simplify, right? Because E equals h nu, and nu equals c over lambda. So substituting in for nu, we can say E is equal to h times c over lambda. And this will now make it very convenient for us to solve for energy. We can now substitute in for h, c, and lambda. And here's Planck's constant times the speed of light divided by lambda. And if we put that all in our calculator, we'll get 3.1 times 10 to the negative 19th joules of energy. Till next time, Crip.